for today we will have Ishaq Aden-Ali from UC Berkeley talk about norms of random tensors and the field application. Yeah.
Great, thanks. Yeah, thanks so much for inviting me, and thank you all for coming. I appreciate it. Yeah, so today I'll talk about norms of random tensors and a few applications, and we'll go somewhat slow and just ask questions if you have them, and hopefully by the end we can get through one short presentation. Cool. So the main character of today are random tensors of the following form. So I'll take T to be tensors of the following form, and I'll call this a Gaussian random tensor because G's will be Gaussians. And here TK is a deterministic tensor, living in this tensor space, right? And so it can be indexed by real values. And each GK is a standard Gaussian random variable, and they'll be independent. Okay. And throughout, we'll use R to denote the order of these tensors and the random tensor. Okay, cool. So this will be a Gaussian random tensor. And here, oh, audio is awful. Okay.
Oh.
Is that
I just saw that it showed up to everybody. Yeah, the audio is a bit low.
okay,
Maybe it's just for me and I can just turn it up.
Is that better?
Can you hear me now?
Yeah. Yes.
I think if you just talk louder, it'll be fine.
Okay, how is that? Is that better?
Yeah, that's better.
Okay, I'll just talk louder. Okay.
All right, thanks. All right.
No problem. So this is a jointly Gaussian random tensor where the TKs will encode some maybe correlation structure, if you will. Okay, cool. So it's a fairly general model, right? And what we want to understand today about these tensors is the so-called LP injective norm. And so for p greater than or equal to 1, the LP injective norm is defined using this inner product here, where the xi's live in the appropriate LP balls. And we take the set of x1 through xr that induces the largest inner product with A in this way, right? Or just for to recollect, this inner product is defined as follows. Okay, very natural, generalizing the matrix case. And for notational simplicity, I like to write it like this. Right? It's a multilinear map from the appropriate bases to reals. Okay. So just for clarity and a recurring theme that in this talk, we'll kind of always look at matrices when we define things, just to get a sense of things. So when A is a matrix, this is nothing but a so-called LP-LQ operator norm. Okay. Okay, so these are generalizing operator norms of matrices to tensors. No, sorry, here Q is the natural conjugate of P. So the main question we want to ask today is, can we bound the expectation or the typical value of this random tensor's injective norm as a function of these deterministic matrices T sub K? We have this random quantity. I want to understand how does it typically behave as a function of the TK. And the answer is yes, using certain variance parameters defined by these TK. So first, let's just look at the definition. Write out the expectation, and what do we get? Well, the expectation is written. Can be written as the following expectation of the supremum, and because things are linear in G here, this is nothing but a Gaussian process indexed by some potentially complicated set, capital S. Okay, so this is just the Gaussian process question, but maybe that's not fair because these can be quite tricky to bound sharply or even at all sometimes. So to define our bounds on this quantity, we're going to have to, unfortunately, introduce some simple notation. Okay, so recall that for a matrix, an order 2 tensor living in that space, there's a really natural contraction taking using a vector x1, taking the matrix A to making it into a vector in dimension g2. And this is can be defined as following. I'm just kind of summing out one of the indices of the tensor or the matrix in this case. And in usual linear algebraic notation, I can maybe write it like this, right? X1 transpose A, L transpose, and I get something like that, right? So more generally, when I have an order R tensor and I have L vectors x1 through xl, I can contract and make a tensor of smaller order in a really natural way. So I can apply like a kind of like a partial application of x1 through xl into the tensor, and I get a smaller tensor. Right, and so now I get a natural order R minus L tensor from the original tensor. Right, and this is, I can write out this giant sum, right, just to make it literal, but it's the really natural thing. I'm kind of like summing out directions using these fixed vectors. Okay, so this notation is nice because I can kind of sum out on the first L coordinates, but of course I maybe want to sum out indices that are arbitrary from 1 through R. And so, or put differently, I just want to contract along arbitrary subsets of indices. Right, so I will kind of define this in a minimally painful way. So we can just consider permuting A using this permutation pi I. And this gives me a new tensor that's just literally a permutation of the tensor. I just shuffle up the indices somehow. Okay. And this permutation pi I is nothing but the simplest permutation that brings up the indices that are arbitrarily spread out between 1 through R and brings them to the front. And the reason we do this is just to kind of notationally define a general contraction, right? So for a tensor A in R vectors x1 through xr, and an arbitrary set I, and any L, I can define the following contracted object, which is nothing but an order R minus L tensor. Right? So what is this saying, basically? I just took the appropriate vectors, L vectors, not necessarily the first L, and just kind of contracted them out and got an R minus L order, like order R minus L tensor. Okay, that's all it's saying. Okay, so that's just a contraction, right? I'm just taking a order R object and bringing it down to a smaller order object. And again, yeah, not necessarily the first L vectors. And the last piece of notation I'll need is very natural and very a generalization of very natural operation we would see in linear algebra. So if I had a matrix, right, square matrix for simplicity, we can also think of this matrix. Maybe this is what you would tell your students not to do in linear algebra, but we can think of it as just a very long vector, right? By just like kind of flattening it along the columns, right? And I get a really long vector, d squared dimensional vector, right? So more generally, I can think of taking the set 1 through 2 and partitioning it into non-empty parts. And for each of the parts that kind of come together into a part in the partition, I'm going to kind of group those together. So flatten along those directions and kind of combine them. Okay? So if I look at the first, there's only two interesting, or two partitions, given the definition. The first one, P1, if I group 1 with itself and 2 with itself, I get nothing back. I get nothing but the original tensor back. And so this is what this notation is saying. I take A to the script P1. Okay, and I get back the same tensor. And the other operation I can define is kind of merging them. And I get back the flattened vector that we just talked about. Okay? Right? And quickly say that it's interesting to look at what the L2 injective norm of these objects are, right? So in the original case, the L2 injective norm is nothing but the operator norm of that matrix. And for the flattened case, I flattened the vector. I looked at the L2 injective norm. That's nothing but the L2 norm of that flattened vector, which is nothing but the Frobenius norm of the original matrix, or the Hilbert-Schmidt norm, if you prefer that. Okay. So if you have any questions, please just stop me. So again, exercise, if I have an order 3 tensor, I can define this partition. What is this doing? It's doing nothing but merging those last 2 coordinates, right? And And lo and behold, I get that tensor that I told you, which is actually just a matrix. Right, and again, I can index them as follows. J1, J2 is just I1 and then the tuple I2, I3. Okay, so very simple operations. And more generally, maybe I'll go through this one quickly. If I,
Can you go back?
Mhm.
Yeah, so I guess the norm of this would be the operating norm from RD to RD squared.
yeah. It'll be the operator norm of this matrix. Yeah, this really square, this really rectangular matrix. Yeah, if I do this operation. Yeah. Okay, so most generally, if I have a square tensor and a non-empty partition, right, I'll get, well, if I apply this partition to the A, I'll get an order L tensor, right? Right, where each of the indices kind of have the dimensionality d to the size of the subset. Right, and it's order L. Okay, so now that we have defined that notation, I can introduce the variance parameters that come up in the bound. So recall that T again is the jointly Gaussian tensor where the TKs are deterministic. So we'll actually have a family of variance parameters corresponding to different orders for the tensors. And these orders range from 0, a scalar, all the way to R. Okay? And so the order L variance parameter of this tensor, which is fully determined by these TK, is this quite large thing, but it looks scarier than it actually is, right? So ignoring this for a moment, ignoring the first sum, what do we have? I have the inner sum, right? Is nothing but, okay, I fix x1 through xr, okay? And I fix k, and then what is this? It's nothing but all order L contractions of tk using the different x1 through xr, okay? Okay, so I just fix the family x1 through xr, and then I'm just kind of contracting this tk into like a smaller dimensional object. And then I look at the Frobenius norm or Hilbert-Schmidt norm of that tensor, right? Squaring, right? So that's all this sum is doing. It's just kind of permuting things, and then I'm just summing out indices.
Yeah, you can write the random tensor T as sum of TK, but with same distribution with different T. So it only depends on the distribution of T, or it doesn't depend on the specific choice of T. You have different TK with the same.
Yeah, this quantity could end up being the same. Yeah.
So it only
Yeah, it
depends
depends.
on distribution, doesn't depend on the specific TK, right?
I'm not sure I understand, but
So you can write sum of GK, and then another sum of GK, but these two things have the same distribution.
I see.
Does it depend on the specific choice of TK or just on the distribution of T?
Actually, yeah, it's a good question. I guess if there must be some equivalence of the TKs if they're going to have the same distribution.
Yes.
Right, and so I'm not sure if that, off the top of my head, if that would be invariant these parameters.
Okay.
But maybe yeah, we'll chat about offline. Right. So yeah, so this is just all the order L contractions I can get from TK using this set of x1 through xr, and then I just take the worst one, and I sum over the k's. Okay, maybe not the best notation, but it is what it is. Okay, so this is the order L variance for a fixed p. Okay, so we're thinking p as larger than or equal to 2. Cool. Okay, so what's the main result today I'm going to share?
Can you go back?
Sure.
To understand. So let's say T is a random matrix. So what does all the 0, and when L equal to 0, what does this give? T is a matrix.
Yeah, when L is 0, it gives you this weak variance. Have you seen this problem?
Right.
We'll talk about it in a bit. We'll get to the matrices. Yes. Okay. Great. Okay, so this is the main result, right? It's somewhat easy to prove, I think, and it's somewhat clean. So it says that for any p greater than or equal to 2 and any parameter beta, like it's like a tuning parameter, we can kind of optimize. And we'll just, for simplicity, consider square tensors. We have that the expected injective norm is upper bounded by this thing. And so what is this thing saying? Right? Perhaps you're not going to get much out of just like staring at it, but we can get a vibe for what it's saying. It's saying that we must pay a price for all of these variances of different orders, but it's nonlinear, right? It's kind of almost like you'll pay based on the order of the tensor.
The square, I mean.
Square, just all the DIs have the same dimension. The square matrix is square tensor. Cube, baby. Right, and so a nice thing about this bound is that when I plug in p equals to 2, perhaps the most interesting case, this dimension term goes away, and it's kind of dimension free, at least explicitly. Right, there's only some implicit dimension dependence based on those variance parameters. And so this formulation is useful, but we can actually optimize this beta parameter using some calculus tricks, and you get this funky looking thing. And what do you get? What is this thing? It's you pay the order 1 variance, and then you pay the worst geometric average of sort of geometric average of the order L greater than 2 variances and the order 0 variance. Okay.
Is this sharp, let's say, when you have a random tensor IID Gaussian entry?
I think so. I think for a square matrix, for example, it'll give you the right thing. Yeah, IID. Yeah. As we'll see in a second. So the natural question is, okay, how does this compare to known results? So we can ask this, how does it compare to known results for the general tensor case, and then kind of a more standard setup like random matrices, like March likes. So first we'll just compare to the existing kind of general results. So a very recent result by Afonso Bandera, Sivankat Gopi, Haotian Jiang, Kevin Luca, and Thomas Rothfuss that appeared in Stock. I think Stock already happened, I'm not sure. Is the following. We showed for any p greater than or equal to 2 and square tensor t, we have the following bound, right? Which is basically, so the variance parameters are slightly different. That's why I put a prime there. But it's again the same kind of phenomena. After applying the square root to the terms, this only is absorbed in this constant here. So here, this squiggly r is just hiding a constant that depends on the order of the tensors, right? But it's almost basically the exact same thing, but they have this kind of term log d here. Okay. And so, how do they prove this result? They prove it using a clever chaining argument based on Dudley's inequality. If that means it doesn't mean something to you, that's okay. And it turns out that even though these variance parameters are not exactly the same as ours, it's not too hard to show that we can always upper bound our variance parameters by theirs. And so our result implies their result immediately, but without this log d factor. So even in the case p equals to 2, there's this log d factor that's somewhat, annoying, and it's not supposed to be there, I guess, based on what we've shown. And the technical reason why it comes up is because Dudley's inequality often gives this an extra log factor. And that's really what's coming up here. Okay, an even older result by Rafael Latała that appeared in the Annals of Probability many years ago, almost 20 years ago, is the following. So I just need to define one more tensor. So remember we had these TKs. What I can define is a tensor at A by stacking the TKs along a new index. And so I get this order R plus 1 tensor. It's not necessarily on the screen anymore. And so if I define A as in that way, I get this order R plus 1 tensor. And what Latała showed is that for any beta greater than or equal to 2, the L2 injective norm can be bounded this way. Okay? And don't worry too much about the details. I think what's most important is that you kind of get the fact that you have to pay this. You kind of have this natural balancing act of this tuning parameter beta and kind of the order of this tensor here that's popping up. Okay, so I'm taking A and I'm making all possible order L tensors from A that's defined here, and I'm kind of weighing them by this scaling factor.
Okay. This is what's called the Gaussian chaos.
It's useful for that, yeah, mostly, yeah. Okay. Yeah, so this paper is actually on Gaussian chaoses, and this is the main technical results used to prove that result. Okay, what can we say about this result? Well, the proof of this result is based using this very interesting but ad hoc chaining argument that's different than Dudley's and Talagrand's majorizing measures theory. And it's not easy to see from here at all, but with some elbow grease, you can show that our result implies this result for the p equals to 2 case, right? Right? In fact, in general, this quantity can be much larger than ours, but we can show that ours is upper bounded by this upper bound. For the, and this, and I should emphasize, this result, as far as I know, only holds for p equals to 2, explicitly in the paper. Okay, so in summary, we have two results. So Latawa's result does not apply, I should say strict inequality, sorry. Does not apply for p greater than 2, but it is dimension free. This result applies for p greater than 2, but it's not dimension free, and we get the best of both worlds. Right?
So you did remove the log factor.
Yes, I did remove the log factor, yeah. Cool. Okay, so now we're gonna get to March's question. So, okay, what happens in the matrix case? Now let's just kind of now that we know that we've kind of recovered all known and improved on, as far as I know, all known bounds for the general tensor case, what do we know about this bound and how it relates to the very classic and well-studied matrix case? Well, in the matrix case, we know, at least for the p equals to 2 case, the usual L2 operator norm, we know that the expected operator norm of a matrix is can be bounded using the non-commutative kinship inequality as follows. So I get these natural variance parameters from those deterministic matrices now, times this root log d factor. And this root log d factor is very different than the log d we saw earlier. That was not necessary. Okay, and this is the gold standard, and this bound is tight in general, except when it's not. And you could talk to March more about that. And so now we know that bound, that's quite good, very good actually. What is our bound in this context? So our bound, we saw that we had the sigma 1 parameter plus, well, this p should be a 2, the sigma 2 parameter, right? Balanced with the sigma 0 parameter. So what happens when you kind of look at the definition and you kind of play around a little bit? You see that the sigma 1 parameter is exactly the variance parameter from the non-commutative kinship inequality, the main variance parameter there. And so we said that, that inequality is tight in general, right? There's a root log factor hitting it, root log dimension factor hitting it. And so here there's no root log d, there's no explicit dimension dependence. Right? So how can that be, right? Did we contradict something? And the answer is no, actually. And so the reason that we don't have the log here is that it's in those cases where the log d is necessary, this quantity in red here is going to be large. Right? So there's no contradiction, right? But the nice thing about this bound is that, in regimes where the log d is not necessary, some such regimes, this will give you the optimal bound. But those are kind of very specialized settings. Okay, but even though this is not the tightest bound in some situations, the natural question is whether we can find some application where the dimension-free bound is crucial. Okay.
About Zoom, okay. That's a local thing.
Oh, is there some comments or? Is someone monitoring the questions?
Yeah, no, those are old, don't worry.
Okay. Okay, cool. So I'll talk about two applications today. The first is related to what Mark said earlier. It's computing or bounding the moments of so-called Gaussian chaoses. So if I let G1 through GR be IID Gaussian vectors, and I let A be some arbitrary tensor, we can define the order R decoupled Gaussian chaos to be the following random variable. Okay, it's defined as basically taking A, the deterministic A, and applying the G1 through GI. Okay, this multilinear map and getting the appropriate scalar out. Okay, so then we'll find SR. And so an interesting and natural question is, okay, when R is 1, this is just basically, a weighted sum of Gaussians, right? And when R equals to 2, this is like taking the bilinear form of a matrix with 2 independent Gaussian vectors. Okay. So a natural question is, in general, for general R, like, what is the value of the pth moment as a function of A? Okay. Where the pth moment, you recall, is defined as this expectation, the pth root of this expectation. So it turns out that actually in the work of Latała that we were citing, his main question that he was trying to understand was exactly that question: what are the moments of the Gaussian chaos? And the result that we cited earlier on the expected injective norm was the main technical result used to prove the following theorem. Okay? What he showed is that there is some constant C sub r that depends only on the order of the tensor, such that for any p greater than or equal to 2, the pth moment can be bounded above and below by this quantity. Right? So this is a tight bound. Right? So this notation is necessary in some sense. Okay? Okay? So what's that? So again, this should hint at you, right? Let's look at the sum here, right? This is where, it's really important to balance out, as this function of p. So you see the right summand, these elements in here are the L2 injective norm of these effectively order L tensors, and the p, the moment bound, like the p that's hitting them has a power that depends on those orders, right? And then this bound is actually tight, it's two-sided up to this C sub r. Okay, again, now we can ask, what happens when r equals to 2? Okay. So I just plug in r equals to 2. There are only two relevant tensors and their injective norms. And when you plug this in and you simplify, you notice that this is nothing but the operator norm of the matrix A times P plus the Frobenius norm of the matrix times root P. Right? And this is actually a very classic result, effectively due to Hanson and Wright. And I think the lower bound was first proven by Latała a few years before his main result. Right? So this is the moment version of the Hanson-Wright inequality. Right? So that general R case generalizes, for general R, we generalize this to higher order chaoses. Okay? But yeah, going back to the main theorem, we see that I want to emphasize that the upper bound is the harder direction, and it turns out that the way to prove the upper bound, there's a really nice inductive argument you can use, and the crucial technical step to close out the induction is to come up with a sharp enough bound on the expected injective norm of a certain Gaussian random tensors. Okay, and then once you have that upper bound, you can plug it into the induction and close the loop. Okay, and basically that inductive procedure is not too complicated. Actually, what actually is really complicated, at least in the original proof, was bounding that expected injective norm. And so when we plug in our bound, we actually our bound that recovers Latała's result. Since the proof of this, our main result, is quite straightforward, we get a very straightforward proof of the entire argument. Okay, at least if you ask me. Okay, so I actually won't go into the proof of those results. I'll just tell you another application that actually motivated me to study this problem. So as someone who sits in a CS department, this is probably the more natural application, a coding theoretic question. And so I'm going to define to you a really nice and natural object called a locally decodable code. So there are two people. There's Alice on the left and Bob on the right. Alice has a message, classic setup. And she wants to send that message to Bob somehow. But there is some sort of noisy channel. And so she needs to add some redundancy to her message and encode it into a longer message. So she'll have an original length little n message, bit string, and she'll encode it into a length capital N bit string, send it through the channel, and on the other end, Bob is going to get the noisy message Y, that is length N, capital N, where a delta fraction of the message is corrupted arbitrarily. Okay, so we make no assumption on how those delta N points are chosen or flipped or not flipped or whatever. We just know that at most delta N points have changed. Okay, now what does Bob want to do? What he wants to do is basically, for any k, he would want to figure out what the kth bit in the original message is. Okay, and so what he does is he will construct, or he'll agree with Alice on the decoder and the encoding scheme, and he'll apply the decoder, he'll flip some coins and pick Q queries from the large message, and using those Q queries that he determined randomly, coordinates the query that he determined randomly, he'll output a guess m hat of the kth bit. And what he'll want for this guess is for it to be equal to the actual kth bit of the original message with some non-trivial probability. Right here, so if I flip a coin arbitrarily, then with half probability I got the right guess, right? So I want to have some non-trivial gamma advantage of decoding the bit. Right, so very simply, Bob just has some randomized scheme of looking at only Q coordinates in the corrupted message and getting the correct bit with some non-trivial advantage. Okay, very natural setup, right? And he wants to be able to do this for every K. So so locally decodable codes were, I guess, formally defined in this work of Katz and Trevisan in 2000. They're implicit in some older works in computer science. But yeah, so we'll call a code mapping n to capital N a Q delta gamma locally decodable code if there's a Q query decoder that is necessarily randomized, such that when it's given access to the bit string Y, for any input message M, for any coordinate K, the probability that the decoder corrects or decodes the kth bit is at least a half plus gamma. Okay, so it has a gamma. Right? And the only condition we'll require on Y is that its Hamming length to the true encoded message is less than or equal to delta N. We make no further assumption. These are very natural objects, very combinatorial objects, I guess. So what do we know about these objects? Okay, so I'll quickly go through this leaderboard with you guys. So for Q equals to 2, we know a very natural construction based on Hadamard codes tells you can kind of make capital N equal to 2 to the little n. It's a fun exercise if you want to think about offline how to do that and why that works, sorry. And it turns out on the lower bound, you can show, or these guys showed, that that's effectively the optimal thing. You cannot beat that. Right? And so, okay, so Q equals to 2, I have this exponential encoding length. Should we hope to get anything better for just 3 queries? Why would that make sense, right? But it turns out that you can do better than exponential. You can do super polynomial sub-exponential, and this was a breakthrough by Sergei Kanin in 2007. He showed a certain construction achieves sub-exponential lengths. That's the actual rate. And what is the lower bound? Well, actually, it turns out that we're very far away. It's not even quadratic, right? It's almost quadratic, lower bound, right? So immediately when we get to Q equals to 3, we have a real difficulty in proving higher lower bounds. Maybe there are better constructions out there, who knows? But there's real challenges when proving a lower bounds. And more generally, for any constant Q, let's say 4 and above, this construction can be kind of extended. And unfortunately, our polynomial lower bound is just failing very fast with Q, right? So even when you plug in 4, things aren't too great, right? And so maybe there are better constructions, or maybe there's a better lower bound. Who knows? And this is actually, I'll emphasize that this n to the q over q minus 2 was kind of based on a sequence of work. So some of this earlier work got it for certain values of q, and then these other follow-up works kind of filled in the gap for the q's that were missing. Okay, so what does this have to do with random tensors? Well, okay, so what I can do is the following. I can show that actually any LDC can basically be, might as well be the following, of the following form. What I'll do is for every bit in the message, I'll make a vertex in some hypergraph. So maybe this is the vertex corresponding to the first bit in the message. And what I'm going to do is pick for each k a different Q uniform hypergraph matching size delta n, which is basically saying I'm just going to pick delta n subsets of size exactly 3 that are disjoint. No point repeats in any of these subsets. Okay. What's the encoder? What does the decoder do? Well, it turns out that once it's fixed this, it's going to flip coins and uniformly at random pick one of these matchings, take the bits that are potentially corrupted and take the XOR of those bits and return that as its guess of MK. And it basically turns out, more or less informally, I'll say, that this is basically the only thing you can do in some sense, or its equivalent. So that's nice. So using that kind of observation, Gopi, S. Gopi, who's one of the authors and one of the results we stated, showed in his PhD thesis that that there are these tensors, deterministic T1 through Tk. Given an LDC, I can define these objects, T1 through Tk, that are order Q tensors, where each of the dimensions is capital N. Okay? And what he showed is given these tensors for a random message, so each epsilon I is a uniformly random Rademacher. He showed that when you push that random message through the encoder, and then I apply this, encoded message. When I take that as a function of the encoder, I get this longer message, and then I apply that to these TKs, and I look at this expectation, right? Epsilon K TK. So basically, some measure of correlation between the encoded message and the original message. When I look at this expectation, you can show that there's some lower bound on it by the definition of this being a LDC. Okay, so basically, I guess maybe I should say succinctly, the encoded message and a random message have a non-trivial correlation as measured this way. Yeah.
So the expectation is on what? What is the random thing?
Epsilon K, so independent Rademacher.
I'm trying to understand that set. Is this set of elementary tensor x1 cross or the?
Oh no, sorry. Just think of this as being like a order Q tensor. Each index is dimension capital N, and it's either 0, 1, or -1.
Okay, let's say Q is equal to what is this set?
It's just a 0, -1, 1 vector. Maybe this notation is. Oh, maybe this is. Okay.
But when Q is equal to its matrix.
Q is 1. Sorry, you said 1.
If Q is 2.
If Q is it's a matrix that has 0, -1, or 1 in the entries. Yeah, it's in that set. Okay, rather than the reals. That makes sense? Okay. So basically, he showed that there's, by definition of the LDC, there's some non-trivial correlation. Okay, that's great. And so I have a lower bound on this expectation. And so what I can do is a very nice, very simple upper bound. So I'm looking at this encoded message. So I just upper bounded by the worst, the supermum in the corners of the hypercube, appropriate hypercube. And then I just normalize. And then when I normalize by n, multiply and divide by n, I get that basically each xk is an element, is going to be an element in the LQ ball, right? And then so I can upper bound that by the expected LQ injective norm. And notice here that we're setting R equals to Q to P. Okay? So the order of the tensor and the LP norm we're computing are the same in this example. Okay, so that's just a valid upper bound in general for any Q. So what happens when you plug in Q equals to 2? Well, that corresponds to a matrix case where I'm looking at the L2 injective norm, which was the operator norm, right? And so I can actually upper bound this thing because I may as well upper bound this by a Gaussian GK, and that can be upper bounded by root n log n. Okay? And I should emphasize and say that the TK has some nice structure on their operator norms. Okay? I kind of skipped that, but. So it turns out that you can upper and lower bound these guys like this, and then when I simplify, remove the capital N, I get this lower bound. Okay? It's a really nice proof, right? You use the non-commutative kinship inequality to prove the lower bound. Okay? It's a very nice proof. I think the earlier proofs were using some sort of quantum argument. Okay. Cool. So it turns out for general Q equals to greater than 3, our main result only implies a lower bound like this. And recall the optimal lower bound I told you about, or the sharpest known lower bound I told you about had a 2 instead of a 1 here, and up to some polylogarithmic factors. And so we can't really recover those bounds or improve on them using the current bound that we had, but this was just wanted to say that this was my main motivation for studying this problem. I will say that this lower bound matches the first general LDC lower bounds by Katz and Trevor when they introduced the paper. And that proof of the lower bound was very, very different than the one that is implied by Gopu's argument combined with our upper bound. And so in summary, if you can get a lower upper bound for random tensors, this immediately implies a higher lower bound for these LDCs, these very combinatorial objects. Cool. Okay, so given all that, I want to just give the very quick proof of our main result. And it turns out that the way we prove our results is very straightforward once we have the following hammer or lemma. Okay, so it's somewhat abstract to say, state, but we'll see how it applies. So if we let Z1 through Zn be independent random variables and define theta, capital theta, to be some subset of Rd that we'll call the parameter space, and let pi be some sort of probability measure over that space that we'll call the prior. And if we fix n functions, f1 through fn, mapping from script z and theta to the reals that are, sufficiently nice, then we have the following funky looking bound. It says that the expectation over Z1 through Zn of supremum of rho of any, like basically the maximizing rho that is absolutely continuous with respect to pi of this quantity is bounded by 0. Okay, so what is this quantity, right? So basically, I'm looking at, for each k, I'm smoothing it, its function, the theta parameter, by sampling from this distribution rho, and I'm smoothing this function using that rho. And here I have some sort of terms that are like non-negative, that kind of control me. So basically, I have some smooth empirical process, right? Basically, where fk zk is an empirical process, and I'm smoothing it with respect to rho. And then I have these kind of almost regularizer terms, right? That are kind of bounding me. And for if I look at the worst case rho, given the realization z1 through zk as Zn, then I can say that this quantity is upper bounded by 0. So this is a very funky looking thing. What does this even mean? And how is it useful? Well, okay. So let's just say you wanted to bound a smooth empirical process that looked like this, right? So I look at, it's almost the exact same thing, but I don't have these minus terms, right? So I look at, for a subset of, let's say, rows that are absolutely continuous with respect to pi, I want to control the following sum, right? Uniformly for all rho and m, and then bound the expectation of that. Okay, how would I use this lemma to bound this quantity? Well, if I can show for any fixed rho uniformly that this expectation of the log MGF quantity is bounded by pk prime, and the other quantity, the KL, for every row is bounded by some b prime prime, then trivially I can lower bound this quantity by some fixed deterministic objects, and then rewrite it so that I could get the upper bound like this. Right? So that's the strategy. I want to bound some process that looks like this, and so if I can bound these quantities uniformly for rho in this set, and then I have a bound. So the name of the game now is, okay, I have such a process. The name of the game now is like, how do I reduce my original process that I told you about, bounding the expected injective norm of the tensors to look like this. Okay. Let's just digest this, right? Like, I want to bound this smooth process. This inequality holds for any row that is absolutely continuous. So if I can say for my subset, surely this inequality holds. So if I can bound each of these guys for my subset, then of course I can rearrange and write the inequality like this. Very simple observation, maybe not so insightful, but it turns out that we can kind of bound these things once we set it up. Okay, so now let's get into the proof. So we have, again, by definition, the injective norm looks like this, right? And so we want to, again, get it to look like a smooth process, right? So, okay, the first step is almost trivial, like it's basically trivial, right? I'll just take xi and introduce some probability measure p sub xi, rho sub xi that has mean little xi. Right? And then by definition, this is literally just the definition of this, the expectation of this vector. And so, that's just the definition, right? But the nice thing is that using the multilinearity of TK, I can pull this expectation out. And it suffices for me to pull this expectation out to have that the xi's are independent. Okay? This is just using the multilinearity of the TK. If the xi's are independent, then I have this kind of product measure, product distribution over the appropriate space. Right? And so now this suggests that, this is going to be our family of measures, these measures rho that are centered at the appropriate x1 through xr. And our parameter space is going to be just the product of the LP balls. Okay? And our zi's in the theorem statement are just going to be the Gaussians. Okay? So I have a natural function, right? This should be my function. Fk, right? Where it's indexed by gk, and these joint this product space x1 times, the product of the LP balls. Cool. Okay, so I have this, very simple identity, right? And so to kind of close the loop, what I need to do is come up with a prior pi and a collection of measures that are centered at x1 through xr, so that I can, again, write it in the formulation that we talked about not too long ago. So what am I going to do? I'm going to do, again, like we said, let theta to be the product of the LP balls. I'm going to set pi to be the RD dimensional Gaussian distribution with scaled identity matrix, where the scaling is 1 over beta. Right? Beta is going to be a tuning parameter. And then rho are going to be, again, the exact same Gaussians, but like shifted. The means are going to be shifted at the appropriate x1 through xr. Right? Very, very natural. And then finally, Fk is going to be defined as follows. It's just going to be, like we said, gk times tk. But now we're going to introduce this lambda parameter that is also another, non-negative real that we're going to tune at the end. Okay? And then M, again, we just need to consider it to be the collection of all possible choices of center for our Gaussian rho. Okay? So in summary, what have we shown? We've shown that the expected supremum that we wanted to bound is equal to the following smooth, the expected supremum of the smooth process, right? Okay? And so now, again, the lambda is just here because we defined Fk to have a lambda in the numerator, right? Okay?
So we don't need the x1 to xr, right? On the right. Rho of x1.
Oh, yeah, sorry, this is a typo, yeah. So maybe I should just write rho of x1, something like that. You don't need it, but yeah. So M is just the collection of all of those rows that are centered at x1 through xr. Okay? And so now we can just apply the lemma, right? And we get the following, right? Straightforwardly. And so what we want to do is bound this expected log MGMF and bound the KL divergence uniformly in this class. Okay? So how do we bound the log MGMF? Okay? So what is this quantity? We're kind of going to condition on the Gaussian perturbation and then look at the log MGMF of the function Fk as a function of Gk. Right? So when I open that, when I open that up, I see that this is nothing, once I condition on rho, this is nothing but the MGMF of a particular Gaussian, right? So I can write the identity, right, from our stats course, and see that this is equal to the log exponential of lambda squared tk theta squared over 2, condition on theta, right? So the log and exponential cancel out, and then all that remains now, when I bring this down, is to compute this expectation. So what is this expectation? This expectation is taking the Gaussian perturbation of x1 through xr for the fixed x1 through xr, and taking the expectation of the square, right? I take the multilinear form, I apply a Gaussian perturbation to each of its inputs, and then I square it and I take the expectation. And it turns out that, it's a little tedious to write out, but once you kind of do the calculations, you open the expectation and you track the sums somewhat carefully, you can see that very naturally, you can upper bound this by the variance parameters that we define from L equals to 0 to R, and the natural scaling beta comes from the choice of Gaussian measure we chose. And those kind of, in the intuition why beta is being powered or is being raised to different powers is that the variances of the Gaussians are going to be multiplying based on the order of the interaction. Okay, so that's just a very simple upper bound on this log of GR. Right. And then the KL is actually quite straightforward. So it turns out there's a closed form formula for the KL divergence between two Gaussians, and it's exactly equal to this in this case, which is the sum of squared L2 norms of the centers divided by 2 times beta. And recall what the XT were. The XT were points in the LP ball, right? And so the largest squared L2 norm a point in the LP ball can have is easy to show, is d to the 1 minus 2 over p, right? And then I just add this up r times. And so that's just the upper bound. So if I put it all together, I get that I can, each of these is my BK, and this is my BK prime and my B prime prime. And I upper bounded my expected supremum this way. And notice that something nice happened. And when I divide by lambda, the KL divides by lambda, but the first term had a lambda squared because of the Gaussian MGF. And so I get a lambda in the numerator on the first term and a lambda in the denominator in the second term. And so I can balance this lambda because I was free to choose it however I wished, so as to get this this square root set. Right, and that's the entire proof of the result. Any question about this? Great. Okay, great. But yeah, so that's everything. And yeah, so I shortened the talk quite a bit, and so I guess that's all. Thanks for your time.
Yep, thanks a lot. I will stop the recording. Feel free to ask questions unrecorded.